How are you today? Today we are going to study the effects of steric hindrance on the nucleophile in SN2 reactions. To serve as a nucleophile, an ion or molecule must get close to a carbon atom to attack it from the backside in SN2 reactions. Bulky groups on the nucleophile hinders this close approach and they slow the reaction rate. For example, if you consider tert butoxide ion and the ethoxide ion, the tert butoxide ion is a stronger base for abstracting protons than ethoxide, but the tert butoxide has 3 methyl groups that hinder any close approach to the electrophilic carbon atom in SN2 reactions. So therefore, ethoxide ion is a stronger nucleophile as compared to the tert butoxide ion. When bulky groups interfere with a reaction by virtue of their size, we call the effect steric hindrance. So when you compare these two ions, tert butoxide is sterically hindered as compared to the ethoxide ion because the oxygen which is bearing the negative charge, which will be shared with the electrophilic carbon, is bonded to a carbon that is bonded to 3 other carbons, whilst the oxygen which is bonded to in ethoxide, the oxygen which is bearing the negative charge is bonded to only 1 other carbon. So it's less sterically hindered as compared to the tert butoxide ion. Steric hindrance has little effect on basicity because basicity involves attack on the unhindered proton. When a nucleophile attack at the carbon atom is involved, however, a bulky base cannot approach the carbon atom easily because remember the electrophilic carbon is also bonded to 4 other atoms. So it's not as easy, it cannot easily access the electrophilic carbon when it has a bulky group. It cannot easily access this electrophilic carbon. So most bases are also nucleophiles capable of attacking either a proton or an electrophilic carbon atom. If we want a species to act as a base, we use a bulky reagent like tert butoxide ion. If we want it to react as a nucleophile, we use a less hindered reagent like ethoxide. Just as the nucleophile is important in SN2 reaction, the structure of the alkyl halide is equally important. We will also refer to the alkyl halide as a substrate where the reaction is taking place, and the compound that is being attacked by the reagent. So that is a substrate, and we've already discussed how the alkyl halide is a substrate. You can also have alcohols as a substrate. In addition to alkyl halides, a variety of other types of compounds serve as substrates in SN2 reactions, and we already discussed that also alcohols and other reagents apart from alcohols and alkyl halides can serve as substrate in SN2 or in nucleophilic substitution reactions. But the only difference, for example, between alkyl halides and alcohols is that, as we have already discussed earlier, is that for the alcohols, the OH group is a poor leaving group, so they are not very good substrates, but you need an additional step to convert the hydroxyl group to better leaving group. Then it can undergo the nucleophilic substitution reactions that alkyl halides undergo. So we will also discuss on the reactivity of substrates in SN2 reactions. So to be a good substrate for SN2 attack by nucleophile, a molecule must have an electrophilic carbon atom with a good leaving group. So this is just common for all those substrates that can be substrates for SN2 reactions. So to be a good substrate for SN2 reaction, then a molecule must have an electrophilic carbon atom with a good leaving group. So for the alkyl halide, the leaving group are the halides. And the carbon has to be electrophilic because it's attached, the carbon is attached to the halogen, which is more electronegative. The carbon is electrophilic. Also in the case of alcohols, the carbon is attached to oxygen, which is more electronegative. So the carbon is electrophilic, but doesn't have a good leaving group. So we need an additional step to convert the hydroxyl group to a better leaving group. But for alkyl halides, the halides have good leaving groups, and also they have an electrophilic carbon, especially at the point of attachment with the halogen. And that carbon must not be too sterically hindered for a nucleophilic attack. This is very important. For SN2 reactions, The carbons which are sterically hindered cannot easily undergo SN2 reaction, where the nucleophile attacks from the back side. There needs to be space for the nucleophile to donate electrons to the back lobe of the sp3 hybridized orbital, which is bonded to the halogen. So you need this carbon not to be sterically hindered. And that's why you find that the best substrate for SN2 reactions are usually methyl halides and primary alkyl halides, which are not so sterically hindered. For secondary alkyl halides, because they have two alkyl groups bonded to the carbon bearing the halogen, they are hindered to some extent. And tertiary alkyl halides, the carbon bearing the halogen is bonded to three other alkyl groups, so it's completely sterically hindered and it does not undergo SN2 reactions. So tertiary alkyl halides do not undergo SN2 reactions. The second requirement is that the leaving group, so we are going to also study on the leaving group effects on the substrate. So a leaving group serves two purposes in the SN2 reaction. So you also need a good leaving group. So, and it serves two purposes in the SN2 reaction. It polarizes the carbon halogen bond, making the carbon atom electrophilic. That one we've already indicated in the earlier sentence. It leaves with a pair of electrons that once bonded it to the electrophilic carbon atom. So it's also important to note that particular leaving group, when you have the atom leaves with the two electrons of the covalent bond that bonded it once to the electrophilic carbon. So it leaves with the two electrons. So, and in the case of alkyl halides, it always leaves as a halide. To fill these roles, a good leaving group must be electron withdrawing to polarize the carbon atom that we have seen for the halogens. They are more electron withdrawing as compared to carbon. And also for alcohols, also the oxygen is more electron withdrawing. So alkyl halides are very good. They are good leaving groups. Not alkyl halides are good leaving groups. They must be stable, not a strong base once it has left. So another requirement for a good leaving group is that once it has left, it has to be relatively stable. Of course, not completely stable because it's got a negative charge, but relatively stable once it has left. Not those which are very reactive, then those ones are not good leaving group, like the hydroxyl group. Once it leaves, it's a very strong base, so it's not a good leaving group. But for the halides, they are very good leaving group because they are not very strong bases. So a leaving group must not be a strong base once it has left with the two electrons of the covalent bond that bonded the halogen to the electrophilic carbon. C, polarizable. So the leaving groups should be polarizable to stabilize the transition state. So that's another requirement. So for example, in the halogen series, if we are to compare the fluoride and the iodide, the fluoride is not polarizable as compared to the iodide, which is the larger ion in the halogen series. So the halide, the iodide is more polarizable, and it's a better leaving group as compared to the fluoride, which is small and is not polarizable, and therefore will not really stabilize the transition state. So this is just more information about the leaving group, or a leaving group, the information where it's elaborated. So the leaving group must be electron withdrawing, that we've already seen in the other sentences, to create a partial positive charge on the carbon atom, making the carbon electrophilic. Then an electron withdrawing leaving group also stabilizes the negatively charged transition state. So that's important that the leaving group is electron withdrawing, so that it also is able to stabilize the negatively charged transition state. So these are strongly polarized bonds. So as we've said, those bonds need to be polarized, the electrophilic carbon. So it has to be bonded to an electronegative atom so that it's polarized, so that it can easily break and leave with the two electrons as a leaving group. Number B, the leaving groups must be very stable once it has left with a pair of electrons that bonded it to the electrophilic carbon. A stable leaving group is needed for favorable energetics. So a leaving group which is stable is very important as compared to those which are not stable. And this is for favorable energetics. So the leaving group is living at the transition state, and a reactive leaving group would raise the energy of transition state, slowing down the reaction. So that is very important to note, that if you have a reactive leaving group like the hydroxide ion, for example, as compared to the halides, then it will raise the energy of transition state, slowing down the reaction. Good leaving groups should be weak bases, therefore they are conjugate bases of strong acids. So when you get the conjugate bases of strong acids are usually weak bases, but the conjugate bases of weak acids are usually very strong bases. So in this case, all the hydrohalic acids are usually strong acids, and most of them, the bases that result from those hydrohalic acids are usually weak bases, like the fluoride, the chloride, the bromide, and the iodide. Those are all weak bases. So they result in two strong conjugate acids. But if you have a weak um, acid, like maybe water, water is also acidic because you have oxygen, which is bonded to two hydrogen atoms, and those two hydrogen atoms have got partial positive charge, so it's acidic to some extent, but it's a very weak acid because when you dissolve, it doesn't easily ionize out. So the bases that result from weak acids are usually very strong. So how you can determine that? So when you want to know whether the base is a strong base or weak, know the conjugate acid. If the conjugate acid is a strong acid, then it will lead to weak bases. If the conjugate acid is a weak acid, then it will lead to strong bases, like water will lead to hydroxide, which ionizes out. And hydroxide is a very strong base, but the acid itself, that is water, is it's a weak acid. But from the strong acids, we get weak bases. So the conjugate bases, or the bases which result from strong conjugate acids, are usually very good leaving groups. But the ones which result from weak acids, or the bases which result from weak acids, are usually very poor leaving groups because they are very strong bases. Other weak bases can also serve as leaving groups, like for example, sulfite ions, sulfonate ions, and phosphate ions. And these are weak bases and good leaving groups. And remember, like for example, sulfate results from ionization of the sulfuric acid. So the conjugate acid of sulfate ions is sulfuric acid, which is a very strong acid. And you can see the conjugate base is a weak base. And also these other ones also result from two very strong acids. So below are the list of some good leaving groups, which are weak bases that are common leaving groups. So the chloride, the bromide, and the iodide. In the halogen series, these are the best leaving groups. And of course, they will always result to strong hydrohalic acids, like hydrochloric, hydrobromic, and hydroiodide acid. These ones are also very weak bases, and the conjugate acids are strong acids. So these ones are also very good leaving groups because they are relatively stable once they leave. So another thing you have to note with these particular groups, leaving group, this category of leaving group, these are very stable because of resonance effect. This negative charge can be used to form a pi bond, and when it forms a pi bond to this sulfur atom, what happens? The pi bond of this, either of this bond to this oxygen or to the other oxygen breaks, and the two electrons now go to this oxygen atom. And later, the third resonance form is where the negative charge will be on this other oxygen. So what it means is that the negative charge is shared by three atoms rather than it being localized on only one atom, like as you can see in the chloride. So these ones are relatively very stable as compared to where the negative charge is localized on only one atom. Here there's resonance effect, the negative charge is shared by more than one atom. In this case, it's shared by oxygen. This oxygen number 1, we can call it number 1. Oxygen number 2, we can call this oxygen number 3. So there are 3 resonance structures where oxygen can be in any of those oxygen atoms. So the charge will be shared by 3 atoms. So that is like dividing it by 3. So it's reduced substantially, and therefore that will make a very good living group. So the same case happens with this other sulfate ion, which is also a good living group. The negative charge is shared between 1, 2, and 3 oxygen atom. What about the phosphate? Here, the negative charge is shared between this atom and this other oxygen atom, not with this. This one has its own, which is localized on it, but either of these can be shared with this other oxygen. So they are actually shared by 2 oxygen atoms. So neutral molecules also are good living groups. There is a way that they live from a molecule. So ions that are strong bases and poor living groups, you have hydroxide. These are very strong bases. This is also a very strong base, and this is a strong base and very poor living group. A neutral molecule often serves as a living group from a positively charged electrophile. So for example, if an alcohol is placed in an acidic solution, the hydroxyl group is protonated, as you've seen in most of when we are reacting alcohols with hydrohalic acids towards the synthesis of alkyl halides, for example. The first step was the hydroxyl group getting protonated. Then after that, it becomes a good living group and leaves as water. So that's what it means. Water then serves as the living group. Then C, finally, a good living group should be polarizable to maintain partial bonding with the carbon atom in the transition state. This bonding helps to stabilize the transition state and reduce the activation energy. The departure of the living group is much like the attack of the nucleophile, except that the bond is breaking rather than forming. Polarizable nucleophiles and polarizable living groups both stabilize the transition state by engaging in more bonding at a longer distance because they are larger ions. So iodide ions, that is one of the most polarizable ion, is both a good nucleophile and also a good living group. In contrast, fluoride ion, which is a very small ion, as we've seen in the halogen series, is a hard ion, and therefore it's not polarizable, so it's not a good living group, neither is it a good nucleophile, as you've seen in earlier lectures. Fluoride ion is both a poor nucleophile in protic solvents and a poor living group in SN2 reactions. So next time we are going to start to cover the steric effects on the substrates. Thank you.